Chapter 14: Rotational and Vibrational Spectroscopy. Virtually everything we know about matter comes from the interaction of matter with electromagnetic radiation. In its most straightforward fashion, such interactions define spectroscopy. Spectroscopy had its origin with Bunsen and Kirchhoff in the early 1860s, as recounted in Chapter 9. Spectroscopy was also an important factor in the development of quantum mechanics, as shown by the Rydberg equation for the spectrum of hydrogen as well as the Bohr theory of hydrogen. Spectroscopy probes energy levels of atoms and molecules; therefore it is an application of quantum mechanics. We have already seen that quantum mechanics provides exact answers for the energies of several ideal systems. What we will find is that many of these ideal systems are useful in understanding spectroscopy, and therefore the energy levels, of atomic molecular systems. Atoms and molecules have energies due to several types of motions. In part, the Born-Oppenheimer approximation from Chapter 12 will be applied. We will treat the various motions of atoms and molecules and the energies of those motions separately. Electronic, nuclear, rotational, and vibrational energy levels can and will be used uh, uh, separately for the most part, although in some cases we will have types of spectroscopy that involve combinations of these energy levels. Conveniently, the transitions that involve the different types of energy levels, electronic, vibrational, and rotational, uh, usually occur in different parts of electromagnetic spectrum. This makes it even easier to consider them separately. We begin our multi-chapter treatment of spectroscopy by considering rotations and vibrations of molecules. Such such motions are considered first for a reason. Both types of motion can be understood in terms of relatively simple quantum mechanics. We will also introduce some tools that we can apply to other forms of spectroscopy. Section 14.1: Synopsis. First, we explore the idea of selection rules, which are quantum mechanical predictions for which energy levels of atomic or molecular system will be a part uh, of a spectral transition. We will see that symmetry considerations are useful for predicting a transition from one energy level to another. Next, we will discuss the electromagnetic spectrum and see how the different forms of spectroscopy relate to the energies of photons. Rotational spectroscopy arises from the quantized rotations of molecules in three-dimensional space. Atoms do not have rotational spectra. However, diatomic molecules have relatively simple rotational spectrum. Since they cannot rotate in two dimensions, a rotation about the internuclear axis cannot be observed, and their behavior of rotation is the same for both directions. Nonlinear polyatomic molecules have 1 for highly symmetric molecules, 2, 3 for most less symmetric species, different rotations in space, complicating the rotational spectrum. Vibrational spectroscopy arises from the vibrations of individual atoms and molecules with respect to each other. The atoms are stretching, bending, or twisting about an imagined equilibrium position. Usually such motions occur at higher frequencies than rotations. So vibrational spectra are observed using higher energy light uh, than in rotational spectra. As with rotations, individual atoms do not have vibrational spectra, because two or more atoms are bonded together and required for a vibration. Like rotations, vibrations occur in certain patterns. However, symmetry of a molecule has greater influence on the number of transitions observed in a vibrational spectrum. Transitions between vibrational energy levels also follow selection rules, which are different from those for rotations. Spectroscopy is a powerful tool for studying matter. The treatment in this text cannot do the topic justice. Series of books are written just on the topics in the next 3 chapters. However, the following material should give you some idea of how spectroscopy aids our understanding of atoms and molecules. Section 14.2 Selection Rules. In spectroscopy, an atomic or molecular system having a certain wave function and energy absorbs or emits energy, usually in the form of light, and in doing so becomes described by a different wave function and energy. In all forms of spectroscopy, it is the difference in energy of wave functions that is the primary observable of interest. Hence, its overwhelming importance to the quantum mechanics. The law of conservation of energy requires that the light, usually in the form of a single photon, have the same energy as the difference in energy of the initial and final states. That is, E final minus E initial is equal to the energy of the photon, or delta E is equal to h nu. Equation 14.1 is written in the original form of the Born frequency condition. The difference in energy of the two quantum states equals the energy of the photon, which equals h nu. Remember, however, that wave functions have symmetry, and so do operators. The light that causes a system to go from one state to another, either by absorption or emission, can be assigned an irreducible representation from the point group of the system of interest. Quantum mechanics defines a specific expression called a transition moment to which an irreducible representation can be applied for an absorption or emission of a photon. The transition moment m is described as m is equal to the integral of psi star final times mu times psi initial d tau. Where mu hat is the electric dipole moment, E is the charge on a particle, and x sub I, y sub I, and z sub I are coordinates for the particle. Transitions of this sort are electric dipole transitions. Transitions between wave functions can be prompted by other interactions, like the magnetic dipole or polarization changes, but the electric dipole transitions are the most common. We can use the conclusions from the previous chapter on symmetry at this point. In order for the integral in equation 14.2 to have a non-zero numerical value, the irreducible representations of the three components of the integral must contain the totally symmetric irreducible representation of the point group of the system, usually labeled as A sub 1. That is equation 14.3. The rate orthogonality theorem may be needed to determine the irreducible representations of the product in equation 14.3. If it contains A sub 1, then the integral may be non-zero and the transition between psi initial and psi final caused by absorption or emission of electromagnetic radiation is considered allowed. On the other hand, if the combination of irreducible representations in equation 14.3 does not contain A sub 1, then the integral defined in the transition moment must be identically zero and the transition cannot occur. It is a forbidden transition. In reality, some forbidden transitions do occur, since the above definition does not take into account the non-ideality of atomic or molecular systems. But forbidden transitions almost always have a lower probability than do allowed transitions. This means that in spectral measurements, absorptions or emissions of radiation due to allowed transitions are typically stronger than forbidden transitions. This fact is not only useful when understanding the spectra, but it also reinforces the usefulness of predictions of symmetry and quantum mechanics. Although the above equations imply a lot of symmetry analysis must be performed, this is not always the case. In equations 14.2 and 14.3, uh, allow for possibility of broad statements about which transitions will and will not be allowed for particular atomic or molecular systems, since such general statements, ultimately based on quantum mechanics and symmetry, are called selection rules. Selection rules allow us to easily determine which transitions will occur. When one is faced with the spectrum to interpret, knowledge of the selection rules is an indispensable tool in deriving physical information from the spectrum. Rotational and vibrational spectroscopy in this chapter are simplified to a large extent thanks to selection rules. Section 14.3, the electromagnetic spectrum. Light can be represented by a wave, like shown in figure 14.1. The wave has a characteristic frequency nu and wavelength lambda, where the two are related to the speed of light, represented by letter C in the equation 14.4. C is equal to lambda times nu. The speed of light in a vacuum is constant at 2.9979 times 10 to the 8th meters per second. The speed of light in a vacuum is a universal constant like Planck's constant. All light, no matter what the frequency or wavelength, travels at this speed in a vacuum. The wavelength has units of length, whereas units of frequency are 1 over s, or s to the negative first. Frequency, thought of as a number of waves of light passing through a certain point per second. Light travels in different speeds through different media, like air or water, but since gases are so dispersed at the speed of light through air is usually treated as the same in a vacuum. This assumption is not valid for the condensed phases like water, glass, or any other type of transparent medium. The quantum theory of light, discussed in Chapter 9, provides a relationship between the energy of light and its frequency. Recall that light of a particular frequency, nu, comes in bundles of energy, which we call photons, having a certain specific amount of energy given by the formula E equals h nu, 14.5. Equations 14.4 and 14.5 allow us to convert between energy, wavelength, and frequency of light. Another convenience for spectroscopists, but perhaps not for students, is the fact that each type of spectroscopy has its own units to indicate energy changes measured by a spectrum. All units are related to energy, but one may have to apply C equals lambda nu or E equals h nu to convert into energy units. Often transitions in microwave regions are stated in units of frequency, megahertz or gigahertz, whereas changes between electronic energies are typically expressed in units of nanometers or angstroms. In both cases, the numerical value and unit collectively refer to the photon that is observed or emitted in the course of transition. Vibrational spectroscopy in the infrared region uses units of micrometers, or microns, to indicate the wavelength of the photon involved in the transition. Microns are typically denoted as mu instead of the SI approved micrometer. Uh, Although the micron is an SI approved unit, the micrometer is preferred. It is often found in scientific literature, therefore you must be familiar with it. Commonly, the wave number is used. It is defined as the number of waves of light per centimeter. So it has a unit of centimeter to the negative first. The SI approved unit for a wave number is meter to the negative first, but centimeter to the negative first is almost used exclusively.